Welcome to lecture 8, which is going to be about hypothesis testing. This specific lecture, I'm going to try to explain it on using PowerPoint slides. And continuing with the next lecture, I'm going to again shift to using pen on the screen kind of method that I've been using all the time. Okay. So first of all, let's go to the very basic construction of a statistical hypothesis. Let me also make this as a laser pointer. All right, construction of a statistical hypothesis. So, while the typical introductory statement in science and engineering, there are usually two or more competing claims, and scientists and engineers need a proper method of deciding which of these claims is more likely to be true. Well, we are going to see that this is the very typical case, and we are that much accustomed to it. We even do not question it. I'm going to try to give examples. And claims about a population parameter is called a statistical hypothesis. Now, this first statement has suddenly turned into a statistical statement. I'll try to explain how this occurs. And the decision-making process is called hypothesis testing. So there are going to be two steps here. Basically, first we are going to talk how a statistical hypothesis is constructed, and well, the straightforward how this constructed, the general architecture is going to be pretty much simple, and then I'm going to talk why that architecture is specifically used. There's going to be a little bit more detail, and then we are going to talk about once this structure is constructed of an hypothesis test, then how do we actually experimentally conduct the test. And this second part is going to be nothing new in relation to what we have learned in terms of probability. It's going to be just application of what we have learned, but in a certain specified manner, whereas the construction of a statistical hypothesis might be the novelty in this chapter. All right, let's just dive into the topic with an example and try to explain these very first two statements on that example. Let's say that we have a chemical company, and we manufacture chemicals in batch mode, and it takes, let's say, 350 minutes on the average to finalize the product. So one product is manufactured on the average in 350 minutes. Now note that in this statement there is nothing like population by mean, or there's no concept related to statistics that we have defined, and this is usually going to be the way that engineers are going to be talking, because statisticians are different from engineers. But note that when you have that information here, and if it is valid, of course, it actually corresponds to population mean. It takes 300, if the engineer is responsible from that process, if they tell you that it takes on the average 350 minutes, it means this process has been running for some time, and that experience obtained from that process, which is actually all that previous data, actually points out that if you draw a distribution from that data, well, actually it's not going to be the population distribution exactly, but still it's going to be a good estimate of 350 minutes as the population mean. So taking this as the population mean, then we say that let's say that there are some units in the process have been replaced by new ones. So there are some renovations in our process, and as the manager of our company, as the owner of the company, we are interested whether that 350 minutes on the average value, not that this is not going to be each product for each product is going to take 350 minutes. Of course, there's going to be a variance, right, between products. And in real life, as I said previously, in real manufacturing processes, we would like this variation as small as possible around the desired value, right? And that's where actually estimations about variation come into role. Why are we maybe interested in variance, population variance? Because we would like this population variance, as I talked about previously, about a detergent in bottle example, right? We would like the height of the detergent, or the volume of the detergent variation as small as possible around the desired value, around the population average mean. Anyway, Here for this question, actually, once we make changes in our process, we would like to see whether that 350 minutes has changed or not. Now, how we are going to test this is going to be the second part, which is related with the decision-making process, which is hypothesis testing. First of all, I would like to convert this question or the scenario here into a statistical hypothesis. Here in this part, we are going to only concentrate on this part. So here, old process mean before the changes is going to be equal to 350 minutes. And note that this is population parameter of the old process, and we may call it we may use mu0 to specify it. Now, the new process mean is mu. Usually we do not use mu0, something like this with a subscript, we use mu. And this is unknown, we do not know this. Actually, the research question is, does mu change or differ from 350 minutes or not? Therefore, this is how the hypothesis test is constructed, the architecture of the hypothesis test. We call H0 as our null hypothesis. Both of these terms are important that you learn them. Null hypothesis is going to be shown with H0. What's that null hypothesis? It is mu is equal to 350 minutes, which is new process mean is equal to 350 minutes. It's like two people arguing on a topic. You may think you having a controversy about that topic here. The first person says mu is equal to 350 minutes. Then there is that person which suggests the alternative, the so-called alternative hypothesis, alternative to alternative to null hypothesis, and he or she says that mu is not equal to 350 minutes. Note that these two span the whole possible region for mu value. So mu is actually a value between minus infinity plus infinity. The first person says that mu is equal to 350 minutes. The second one, note that he or she does not say anything about an equality. Actually, this is an inequality. No, it is not equal to 350 minutes. This is what we call two-sided hypothesis test. Why do we call it two-sided? This is just like confidence interval concept, and we are going to, in this chapter, we are going to talk how to combine confidence interval and statistical hypothesis, and you are going to see that they actually answer the same question but from two different perspectives. Anyway, two-sided hypothesis test, because either mu is smaller than 350, right, this value, or mu is greater than 350, both of these cases will be valid in terms of alternative hypothesis. So for the guy who suggests the alternative hypothesis, actually both cases are valid. So this is called a two-sided hypothesis test. Note that H0 is our null hypothesis is always shown as an equality here. And the alternative hypothesis, I think I forgot to mention that it's named as H1, is always shown as an inequality. This is a pretty much important concept I'd like to talk about probably in less than 10 minutes, within 10 minutes. Okay, so a second example. A new drug is suggested to be effective in flu treatment, a pretty much daily event, or not maybe exactly this one, but related with the coronavirus and the treatment, possible treatment or vaccine studies. Anyway, and we would like to test this claim. So this may be easily adapted to coronavirus. Somebody comes out with a vaccine or a treatment, and he say or she says that this is effective in coronavirus. Okay, but let's leave it in flu. And it is known that it takes 5 days on the average to recover flu without any treatment. Now, this information, if it is valid, and actually I just made it up, of course, based on some experience, but I need more scientific evidence for that. Anyway, this corresponds to note that the population average, when it takes 5 days on the average to recover from flu without any treatment, there are a population of people, a hypothetical population of people who have the flu, but who do not use any treatment. And from that population, weighted with respect to their corresponding probability density function, it takes 5 days. The population mean is equal to 5 days. Of course, they are going to have variances. So there may be some people who recover from flu in 2 days or some in 15 days. There's going to be variance, but the average is the population mean is equal to 5 days. So now question is, test the effectiveness. How are we going to test the effectiveness of the drug? All right. So again, let's liken it to the previous example. Old process mean here. So think about that. Old process is the people with the flu, but with no drug. Mean recovery time is 5 days, and we can call it again mu0. And new process mean is the mean of the recovery time of people who use that drug under treatment. And we are going to call it mu, which is unknown. So here is the construction of the hypothesis test. But before that, the question is important. Well, actually here the question is, compared to the previous one, actually, is the new drug effective? Now there's an important point here. When we say, is the new drug effective, we do not exactly mean that, or if you like, you can take it that meaning, but probably it's not usually when it comes to health issues. It doesn't mean that we would like to check whether mu is equal to 5 or mu is not equal to 5. If the mean recovery time under treatment is greater than 5, let's say is found to be equal to 7, it means that, all right, the drug is effective in a way, but it affects in a bad manner. I mean, if you hadn't used that drug, the average time of recovery would have been smaller. So that effect is a side effect, or it has a bad effect. So it's that it doesn't have a good effect. It doesn't have the effect that is expected from a drug. So basically, if you really would like to test the drug, the question is whether you can lower this mu value, the mu value of this the recovery time of the people using that drug in shorter than 5 days of time. So in this case, the null hypothesis will be again the equality that mu is equal to 5 days, right? Mu, what we do not know, but we just assume that it is 5 days equal to 5 days. The alternative hypothesis will be mu is going to be smaller than 5 days. Well, you may say that, didn't I say that we divide the whole space into 2 of mu being between minus infinity to plus infinity, and we divide the whole space into 2, and this here, it doesn't seem to be so, because what about mu greater than 5 days region? Actually, it is also included in null hypothesis. Please always use mu is equal to 5 days. Use an equal sign here for the null hypothesis, but for this case, where you use a smaller or greater than value, compare it to this not equal to sign. Not equal to because it includes every point except mu is equal to this specific value. Here, actually, this only includes mu is smaller than 5. Therefore, there is a hidden greater than sign also there. So it's going to be mu is greater than that or equal to 5 days. But please do not show it that way. Take it as mu is equal to 5 days. And these are called one-sided hypothesis tests. Very similar to one-sided confidence bounds. We are only interested in deviations in one side. If mu is greater than 5 days, I don't care about it, because actually, if its mu is not smaller than 5 days, right, we are not going to be using this this drug, whether mu is equal to 5 days or even mu is equal to 10 days, because it is not effective, means it does not decrease the treatment or the recovery time. Whether it increases or it's not, it doesn't affect, I don't care about this. Well, one may be caring about that, but for this specific question, we don't care about this. So here we have in alternative hypothesis, another inequality representation. So this is basically the representation of an hypothesis test, or the construction of an hypothesis test. So in this hypothesis test, the architecture, and let's remark a couple of points. First of all, hypothesis test is always about a population parameter. Here in this example, and also in the previous example, I have not talked about sample mean. I have always talked about population mean. So it is always a population mean under scrutiny. This thing, or maybe population variance, or maybe for a Bernoulli process, population parameter P, or for an Poisson or an exponential process is going to be lambda. So it's always going to be about a population parameter. It's not the sample variance, it's not a sample mean, it's not the proportion of positives in a sample as X bar in what we have covered in the previous lecture at the very end of the previous lecture. So it's not about a sample statistic. So you may ask, aren't we going to use sample statistic? Yes, we are going to use when it comes to conducting the hypothesis test. So as a kind of what we are going to cover in the forthcoming slides, construction of the statistical hypothesis will be on parameters, population parameters, whereas the decision-making process, the testing itself, will include samples and sample statistics, estimators, their properties, all those stuff. Now we are only concentrating on this part, statistical, how to construct the hypothesis itself. So this is the first remark that I would like to point out. And the second remark is actually this decision about the hypothesis test is made using a test statistic on a sample. I have already talked about. Actually, I have both combined those two remarks as one, but actually those two separate remarks. All right. And the third one, and this is going to be in question related, why do we construct the hypothesis test in this manner? As I said, I think about 5 minutes before I said that I'm going to talk about, probably in 10 minutes, I will. Well, couldn't we have changed this H0 and H1? Couldn't we say that here H0 is the null hypothesis mu is smaller than 5 days, and the alternative hypothesis mu is equal to 5 days? The short answer is no. And that's actually a little bit of a philosophical issue, but actually in this hypothesis testing, that philosophical issue should be discussed, which I will after this. Now here, but let's just say that burden of proof always lies on the alternative hypothesis. Let's see what this is. First of all, in some researches, this alternative hypothesis, or in many researches, this is first of all called research hypothesis. Let's go one step further. Usually the interesting hypothesis is this one. This is the novelty this is the new guy in town. Think about it like that. This is the old, what we call status quo. Well, you think that this is the case, but somebody comes and says that, no, this might be the case. This is the general architecture. So when we have this as the new case, the suggested, the hypothesized new state, this alternative hypothesis has the burden of proof. If somebody suggests an alternative, he or she has the burden of proof, which means he or she has to prove that this is the case. That may seem interesting. The null hypothesis does not feel the need to prove itself. That's going to be a subtle point, which I'm going to be talking about now. Now, how to perform a hypothesis test? I'm not sure whether to continue with the philosophy of the hypothesis, architecture of the hypothesis test, specifically why H0 is H0 and H1 is H1. But let's leave that to the next topic. Let me go with the more practical issue. So I'm going to continue with the second part. Once we construct the hypothesis test properly, two hypotheses properly, how do we conduct the hypothesis test? Then I'm going to return to that philosophical issue. So let's say that we have a company which produces specialized chemical, and the active ingredient, is this ingredient spelled correctly? I'm not sure. Anyway, in the chemical is required to be equal to 3.0 kilomoles per meter cube. Let's say that law states that I produce, a manufacturer a specified chemical, and a certain substance inside each of my products should be equal to 3 kilomoles per meter cube. I just made it up. So here, the true value of mu in our product, the population mu, should be equal to 3 kilomoles per meter cube. Note that this does not say anything about variance, but note that, as I said earlier, variance should be as small as possible so that each of my product is going to have an active ingredient value close to this one. specified by the law. But this specification by the law is actually should reveal itself in my population mean. So population mean should be equal to 3.0. However, let's say that there is an inspector from the state and who suspects that my product does not, the population mean of my product is not equal to this value suggested or proposed by the state laws. So in this case, how are we going to test that whether my products the population mean of the active ingredient in my products is equal to this 3.0 or not? So first of all, what we should do is we should construct a hypothesis test. So here the null hypothesis, the general brief status quo, I may say, is my population mean is equal to 3.0 kilomoles per meter cube. The alternative hypothesis, which is suggested by the inspector, is mu is not equal to 3.0 kilomoles per meter cube. Could we have changed those? No, we couldn't have changed those. Now, the burden of proof is in alternative hypothesis. This alternative hypothesis should prove that this is the case, not the null hypothesis. All right, so what we do is this. Well, prior to taking a sample, but determining the sample size prior to this. So once we construct this hypothesis test, still we haven't taken a sample, we then say that what is going to be the sample size that we are going to use to test this hypothesis. Well, the sample size is just a random number. No, it is based on some statistical considerations also, but I'm going to leave that here. For instance, we are going to say that we are going to take 16 observations. So we take 16 individual specimens from our 16 randomly selected products and form our sample. Assume that that is the case, or 25 or any number, I don't know. Now, depending on this sample size, and before, let's say that taking that sample, but when we decide that sample size, and I'm going to show you how, we also determine an acceptance region. What do I mean by that? This is a region just on the left-hand side and on the right-hand side of the hypothesized mu value. Here, mu 0 is equal to 3.0, where mu 0 is the hypothesized value, null hypothesis value of mu. We suggest that null hypothesis is true. So here is the point. Assuming that null hypothesis is true, note that alternative hypothesis should show itself that this isn't the case, and until this is so, I'm going to assume that this is true. So assuming that null hypothesis is true, therefore mu is equal to mu 0, which is equal to 3.0. So around that, we are going to have an acceptance region. How are we going to obtain this acceptance region? Based on the sample size, based on the sampling, based on the standard error of my estimator, I'm going to determine this, which I'm going to talk about in the next lecture. It's something that we already know, no big deal. Let's say that we have determined that region to be equal to between 2.6 and 3.4. These points will be critical values. This is going to be the lower critical value. This is going to be upper critical value. Note that they are very similar to confidence intervals that we talked previously. However, there is an important difference I'm going to talk about later, because this is around the hypothesized value. Note that on the other hand, the confidence interval was around or was about the sample estimate or sample statistic that we were using. Anyway, so around this hypothesized value, we form an acceptance region, what we call. And outside this region, there's going to be a critical region. How do we use that, or why do we name acceptance in a region? I'll talk about. Now we choose a randomly selected sample of n specimen, right? Random choosing is again important. And from that sample, we obtain a X bar value. In each of these samples product, we measure the active ingredient inside, and then using each of these x1, x2 to xn, and finding X bar value. The next thing that we do is if this x bar value lies in this region. So what's that got to do with the null hypothesis? Note that here is the issue. Considering that this is true, you expect that any sample mean should fall around this value, 3.0. How much around is going to depend on sample size. It's going to depend on sampling variance of x bar, which is standard error of x bar, all those things, but it should be around this value. So if you are around this value, we say that we do not reject the null hypothesis. Now here is an interesting point which I'm going to consider next with the also architecture of this. Why do we use H0 or H1 here? We do not say we accept H0. We do not say we accept the null hypothesis. We do not say we prove the null hypothesis. We say we do not reject or we cannot reject. The typical way of saying in statistical terms, there is insufficient evidence to suggest that mu is not equal to 3.0 kilomoles per meter cube. That may be a little bit overwrought statement maybe at first sight, at first time you hear it, but actually in statistical terms that is a pretty much valid statement. And you cannot say that mu is equal to 3.0 kilomoles per meter cube is proved or is accepted. I'll come to that. That's the reason why this is called a weak conclusion. Because we simply say that we do not reject this, or we cannot show that mu is not equal to 3.0 is valid. That's why this is called a weak conclusion. Why is this a weak conclusion? I'm going to explain with this properties of these H0 and H1. If on the other hand, x bar value falls in critical region, here smaller than 2.6 and 3.4. In practical terms, this means x bar value is far from the hypothesized value, which is the hypothesized value in H0, in null hypothesis. This should point out that the hypothesized distribution here, because its mu value was equal to this one, and we have that except this region, this is not valid. Therefore, if all of the rest of the assumptions are related to, for instance, normal the distributional properties of the estimator and all of them are true, the thing which is not valid is this one, which means our mu is now not equal to 3.0. So if x bar lies here or here, we say that mu is not equal to 3.0. So we show the validity or truth of this statement. I don't want to emphasize this too much because these are all probabilistic statements. So this is true, but with respect to some probability still. But still there is going to be a non-symmetry between those two. Here when x bar lies here, we show the validity of this statement and we say that we reject the null hypothesis. We show that this is incorrect. So mu is not equal to 3.0 kilomoles per meter cube. Then this is called a strong conclusion. On the other hand, when we are in the acceptance region, we do not say that we accept mu is equal to 3.0. On the other hand, here we may say that mu is not equal to 3.0. Here we do not say mu is equal to 3.0, but we simply say that we cannot reject this hypothesis. So please be careful about this non-symmetry between strong conclusion and weak conclusion. While alternative hypothesis needs burden of proof, but that once you have the proof, it is a stronger conclusion. That is the advantage. So that's why we have these research hypotheses. They are difficult to show, to validate, but on the other hand, once you validate it, it's a stronger conclusion. If on the other hand, if you show that this is not let's say that you are in the acceptance region, you just simply say that this is not true, it's not the conclusion. You say that we cannot reject this null hypothesis in favor of alternative hypothesis. So now let's try to combine this weak conclusion, strong conclusion concept here with the order of these. Why do we use an equality here and non-equality here? All of them are pretty much connected. So I'll try to explain this on a paper of Ronald Fisher. All right, so let me just make it slightly larger and let's see. All right, so this is a paper from Ronald Fisher, I think 1950, yeah, it says 56. Mathematics of a Lady Tasting Tea. This is an interesting story, statistical story, or historical statistical story, I may say. Please Google it. It is basically maybe an fictitious event, maybe a real event. There is also a book that you may find in library. It's an interesting book about history of modern statistics, and some part of it's really actually about the lady tasting tea and Ronald Fisher. I think that was a kind of a real event, but I don't know. I cannot be sure about 100% since this is a statistical course. Okay, so the whether fictitious or real, the event explained by Fisher here is this. A lady declares that by tasting a cup of tea made with milk, she can discriminate whether the milk or the tea infusion was added first to the cup. So the idea is somebody comes and say that, okay, if you have a tea with milk, if you just give it to me, right? And when I taste it, I can say that that tea or milk was added first. And this is what, well, it's a kind of interesting suggestion. And this is what Ronald Fisher would like to test. Can I come up with a statistical method to test this hypothesis, whether there is some truth in what this lady is saying, or this lady is totally a fraud? This is the thing that Fisher is trying to determine. And there's actually the whole paper is about that. And this is basically the hypothesis test concept that I've already talked about, because he is the guy who come up with hypothesis test. And here there is actually a paragraph. Now, since I skipped the whole thing, basically how he construct the hypothesis is by this way. The null hypothesis is no sensory discrimination, which means the lady does not have any special power. He or she only just assumes that tea is first or milk is first, and sometimes they just happen to be the correct order, and people seem to think that she has some sensory discrimination about this event. And the alternative hypothesis is no, she has really indeed some sensory discrimination. This is the way he constructs the hypothesis. And note that this also fits to the previous explanation I tried to come up with in terms of hypothesis test. When we have H0 is the status quo, the default belief, whereas H1 is the new guy in town. It's a research hypothesis. It's a novelty. So the typical case, the conventional belief probably is no sensory discrimination power, whereas the research hypothesis is no, she has some X-Men kind of, mutant kind of powers. Okay, so what Fisher says here is this. Well, it's not very easy to understand what Fisher said, because he doesn't write everything in too much detail. Of course, he doesn't need to, since he has come up with all this stuff, and he's the probably one of the great geniuses of 20th century, but that's how he does. It might be argued that if an experiment can disprove the hypothesis that the subject possesses no sensory discrimination between two different sorts of objects, so it can disprove H0, which is going to lead to H1. No sensory discrimination can be disproved. If you can come up with that test, he says, right, it must therefore be able to prove the opposite hypothesis, that she can make some such discrimination. Okay, what I mean is this: if your X bar value comes out to be in the critical region, then your H0 will be rejected, and you are going to accept H1. If this is the case, then naively one may say that, okay, we may change these order of these two and work the same way. And he says this, but this last hypothesis, however reasonable or true it may be, is ineligible as a null hypothesis to be tested by experiment, because it is inexact. Because if you write this as here, this one as H0 and this one as H1. Now note that some sensory discrimination is not an equality, whereas no sensory discrimination is an equality. Some power is equal to 0, whereas this one says some power is not equal to 0. If you put it that way, then how can you come up with an experiment that you can reject H0? This is what it says. If it were asserted that the subject would never be wrong in our judgments, we should again have an exact hypothesis. Actually, what he says is, in this form, it's not possible to devise an experiment, devise actually some interval, some critical regions and accepted regions, because it says some sensory discrimination. It's not an equality. When it's not an equality, we have a problem. He here suggests that instead of this, you may say full sensory discrimination. Now in this case, you can test this null hypothesis, because full sensory discrimination is going to mean that he or she, in every case, she has to find it, that lady, she has to find the true order. Now this form is convenient for an null hypothesis. Alternative hypothesis, but note that here is not is not convenient, because these two, H0 and H1, do not span the whole space. Full sensory discrimination, okay, she should predict the order in all cases. No sensory discrimination, however, corresponds to she should predict in no cases. But what if she predicts this for, let's say, 60% of the cases? These two, H0 and H1, do not span the whole possible regions of outcomes, I may say. Therefore, in this case, we are going to write here some sensory discrimination. So here H0 should be equal to full sensory discrimination. She predicts it perfectly. Then H1 is going to be some sensory discrimination. No, she does not predict perfectly. So one may say, why don't we use this form? Because this form is not very much realistic with respect to our expectations. Note that what we expect, since we are living in a non-X-Men universe, right? And pretty much what we see in your daily life, that not that much interesting. Our null expectation is not those special powers, but no special powers. So H1 would be, yes, there may be some of them is due to special powers. So that is, the other one is a more realistic way of conducting the hypothesis best, but in terms of statistics, this is also valid. So the moral of the whole story is even that the null hypothesis must be exact, that is free from vagueness and ambiguity, because it must supply the basis of problem of distribution, of which the test of significance is the solution. Now this part, maybe the wording is a little complicated, but it simply says that it should be an equality such that, remember here, let me again come back to the PowerPoint presentation here. Okay, now the only way that we can construct something like this is we should have this value here exactly, and this is given by the null hypothesis. If you don't have this exactness here, then you will not have exact an acceptance region and exact critical region here. And if you would not have that, then you would not be able to conduct this hypothesis test. That's why equality is to be put in the null hypothesis. Well, there is another issue related with that. I'm not going into the details of this, but I'm going to just actually show you the direction, I may say. What do I mean by show you the direction? Actually, I'm just going to show you a philosopher who is in very close period, close to Fisher. He came up with this idea, if I can show him. Yes, you can find, his name is Karl Popper. The idea is very simple. He says that it is never possible to prove a scientific hypothesis, but you can disprove it using a single observation. And this is very much connected to the hypothesis test concept. The reason why the equality, the null hypothesis, even when we are in the acceptance region, we do not say that we prove that or we show that the null hypothesis is true, is because being in the acceptance region does not necessarily show that it is true. It means that we haven't been able to invalidate this hypothesis yet. Note that the null hypothesis is an equality, the other one is an inequality. So an inequality might be proved, showing that that equality is not valid. But where on this inequality, in which region you are exactly, is still going to be unknowable. So basically, it is a combination of that concept that Fisher has come out that equality should be in the null hypothesis. And why do we but while we say we reject the null hypothesis, why don't we say we accept the null hypothesis? Because the null hypothesis, due to basically the philosophy of Karl Popper, the 100% validation, confirmation, or proof of scientific hypothesis is not possible. Even, for instance, Einstein's theories about gravitation are still being tested. And from these tests, actually, they find that they cannot reject these hypotheses or these theories yet, but in the future, there may be some observations which may reject those hypotheses. So when it comes to statistical hypothesis test, it's only the test that either reject the current hypothesis or that cannot reject. It's not used for proving. This is the idea. Now, as a further example, and I think a kind of an interesting example, I would like to talk about the, let me again put on the, well, actually, I don't need to put anything on the screen because this is not anything from PowerPoint. So example maybe from the jury system in the United States. We have watched many Hollywood movies, so we are aware of the whole system, I guess. So at the end of the trial, the jury comes and the head of the jury says that probably what you remember is the convict is innocent or guilty. Well, actually, he never says innocent. That person, the speaker, he or she says not guilty or guilty. Now, that's an interesting thing if you are also interested in the logic of law or the philosophy of law, and this is very much related with hypothesis test. So let's try to think about let's try to put the whole trial procedure into an hypothesis test. Now, H0, the null hypothesis at the beginning of a trial is that person is innocent. No, the null hypothesis is that person is not guilty. I'll talk about the innocence versus not guilty in a minute. And it's again related with hypothesis test. And the alternative hypothesis is H1 is that person is guilty. The trial goes on, all these lawyers and blah, blah kind of thing. And at the end, the result is either H1, which is that person is guilty. What do I mean by that? Actually, that's the research question. Therefore, their burden of proof lies in showing that that person is guilty, H1, right? So if there is sufficient evidence corresponding to you are in the critical region, you are far away from the hypothesized value. And here the hypothesized value is that person is not guilty. If you are far away from that, and how is that possible in terms of a trial? There are some evidences showing that that person is far from being not guilty. So in this case, the jury says that that person is guilty. On the other hand, the other option is if they cannot find sufficient evidence to support the alternative hypothesis that the person is guilty, that the research question is that the person is guilty, what they say is not the person is innocent. You may also take it as the alternate, the null hypothesis, which means accepting the null hypothesis, but they say that we cannot show the guiltiness of that person correspondingly not guilty. So it is not a acceptance of innocence, but it is a kind of not being able to show that that person is guilty. Please watch these movies if you are interested. There are many details in those Hollywood movies. Usually lawyers try to, I especially recommend for those who haven't watched the American crime story, O.J. Simpson case. I think that was a very interesting TV show, about 9 or 10 episodes. Anyway, what lawyers usually try to come up with is reasonable doubt about the guiltiness. If you can put that in the mind of the jury, then that means that you are not in the critical zone. Then the jury finds the result not to be in the critical zone, but the acceptable zone. But as I said earlier, acceptable zone does not mean that that person is innocent. It means that there is not sufficient evidence to suggest that that person is guilty. Okay, that's all.